This video, I'm going to go through our notes for section 1.3, and this is over using ratios to solve equations. So, before we start, probably need to talk a little bit about what a ratio is. And a ratio is when we compare two values. So for example, we might say the ratio of students to teachers in a class is 15 to 1. This is a common statistics you might hear, and the way that we would normally say that is that the student to teacher ratio is 15 to 1. And that order matters. So if I say student to teacher, and then I say 15 to 1, that means that for every 15 students, there is one teacher. Proportions are where we can write an equation where two ratios are equal. So if we thought about that 15 to 1 ratio of students to teachers, we could say, well, this would be equal to another ratio where maybe we have 5 teachers, but I don't know how many students that would be. So since this is a proportion, we know that these things are equal, they're the same, and we can use that idea to solve for this missing value. So that's what we're going to get to here in just a couple minutes. Some of these times, we're going to have to set up our own proportions, kind of like we're going to do here in example 1. It says the right triangles created by each object and its shadow are similar. And the question is, can the tree fall onto the house? So we have our tree, and its shadow has a length of 30 feet. And we're comparing that to this person over here who's 6 foot tall, and they have a shadow of 8 feet. The tree is sitting 25 feet from the house, and we need to figure out if this tree were to fall over, would it actually hit the house? That's the question. And so obviously we need to know the height of the tree, because if it's over 25 feet, then it would hit the house. But if the height of the tree is less than 25 feet, then it would not hit the house. And we're going to use this idea of similar triangles to figure this out. And the main idea here is that similar triangles are proportional, meaning I can set up this equation using two ratios where I can compare the shadows of the objects to the actual height of the objects. So that ratio would look something like this. The shadow of the tree is 30 compared to the shadow of the person, which is 8, must be equal to the height of the object, which we're calling h, right? Here's my h for height. And then I'm going to compare that to the actual height of the person. So what we're comparing is the shadow compared to the actual. And since these are similar triangles, that's going to equal the shadow compared to the actual. And just for clutter's sake, I'm just going to get that out of here. To solve this proportion, this is just really a one-step equation. We're just dealing with fractions, which I know can be challenging for some of us sometimes. So I'm trying to find the value of h. I'm trying to get that h by itself. Right now, I have h divided by 6. So in order to undo that division and just get that h all by itself, we just need to multiply both sides by 6. And normally I would just kind of show that by doing something like this. But again, just for the sake of clutter, I'm going to get that out of here and then just kind of show what happens down here below. So if I multiply by 6 on the left, we would have that 6 over 1 times 30 over 8. And on the right, when I multiply by 6, we're just left with h. That was the whole reason that we did this in the first place. right? So we would just have the height. I wrote this 6 as 6 over 1 because when I multiply fractions, it's always easier for me to think of both numbers as a fraction. And the whole number 6 means that I've got 6 over 1. That means the same thing, right? It's the 6 would be on the top if this were a fraction. So when I multiply those straight across, right, when we multiply two fractions, we multiply straight across. So the top times the top, and I can still write this as equal because all of these things are still equal. 6 times 30 is 180. And on the bottom of the fraction, we have 1 times 8, which is 8. When we get here, this doesn't really reduce nicely, but we could punch this into a calculator. Remember, fractions and division are the exact same thing, so I could just do 80 divided by 8, and we would get 22.5. So the height of the tree is 22.5. Is that going to hit the house? Well, the tree is 25 feet from the house, so we are safe. It should not hit the house if it falls over. Here's a big key to doing problems like this. It gets a lot messier if the variable is on the bottom and we're trying to do stuff to both sides. If we flip both of our ratios, we will end up with something that means the exact same thing. So the hint is, if the variable in our proportion is on the bottom, we can flip both. So for example, if I had this, 8 over x equals 5 over 3, I can flip both of these. So notice that becomes x over 8, and then the other one becomes 3 over 5, and I still end up with the same proportion. And now I still have that same one-step equation. So since my variable is x, and then I've got x divided by 8, to get x by itself, I would just multiply both sides by 8. And it would end up working out just like this. Okay, moving on to our next idea here. We can analyze some statistics using different rates. So comparing performances in 2019 to 2020, and rates we use to compare things with different units. So for example, like if you're thinking about gas mileage in your car, miles per gallon is a rate. Or if we're thinking about speed, we would have miles per hour. So anytime we're comparing two different units. And what we're going to look at here is we're going to look at hits per strikeout. So if we're comparing this pitcher's statistics, so how many hits did they give up compared to how many strikeouts they had. And again, this order matters. If I say hits per strikeout, we're still thinking of this as a fraction where the number of hits are on the top and the number of strikeouts are on the bottom. And I'm going to use the variable K to represent strikeouts because that's a common thing that we'll use in baseball, so that makes sense, and it'll save us on some writing. So let's look at for 2019, gave up 54 hits and had 100 strikeouts. So for 2019, our ratio of hits per strikeout would be 54 over 100. And again, let's just punch that into our calculator as division. 54 divided by 100, and you end up with 0.54 hits per strikeout. So that means for every one strikeout, this pitcher gave up 0.54 hits. In 2020, hits are, let's just switch colors here. Hits are 42, strikeouts are 73. So again, we just set up our fraction. Hits 42 per strikeouts 73. And if we punch that into a calculator, we would get our number here. And I didn't do that in advance, so give me just a second. This should be 0.57. Not 7.5, 5.7 hits per strikeout. Okay, so the question is, which one is better? Obviously, these are pretty close. So in 2019, he gave up 0.54 hits for every one strikeout, and in 2020, gave up 0.57 hits per strikeout. And you kind of got to know a little bit about baseball to know which one of these are better. Pitchers don't want to give up hits, and they do want strikeouts. So the lower number would be better. This would be giving up less hits compared to the number of strikeouts. And we could compare almost any of these statistics, right? How many earned runs per inning or how many walks per inning. Those would be good statistics if we were analyzing this pitcher's effectiveness. Okay, and then the final topic in section 3 is conversions. So we'll just jump right into our first example here. We're going to convert 4.8 gallons into ounces. And then it tells us here that there are 128 ounces in a gallon. This is what we call our conversion rate. So that's what's going to allow us to make the change from gallons to ounces. And when we do this, you're going to notice that we need to be careful with the way that we set this up with our units. And this will make more sense in just a second. So whatever the units are on the top, originally, we need to have that same unit on the bottom of the next ratio. So I'm actually just going to get rid of this for a second because that's for another example we're going to do here. So if I have 4.8 gallons, if I want to convert that into ounces, I'm going to use multiplication, and I'm going to use my conversion rate. And here's what I was talking about with the units. If I want to convert from gallons, my rate has to have gallons on the bottom and then something else on the top. If I can just go to ounces in one shot, that's great, like we're going to do now, but sometimes there are going to have to be additional steps in between. So ounces on top, gallons on the bottom. And it might help to fill in those units first and then put in the numbers. Because what this is telling me is 128 ounces in a gallon, so that's 1 gallon. And then once you've got that all filled in, we just do the multiplication. Remember, this is just going to be over 1, so if we're thinking of everything as a fraction, we're going to multiply straight across. So 4.8 times 128. And again, I don't have this handy. 4.8 times 128 equals 614.4. Okay, so in 4.8 gallons, there are 614.4 ounces. So again, I want to show you a little bit further example because we can do this. We can do this with units on the top and the bottom, and we are going to have to change both. Or we can do this where we have more than one step. For example, I was going to do this, not feet, 5.5 feet. And say I want to say I wanted to change let's say 5.5 feet into centimeters. Okay. Maybe I don't know how to do that in one step, but if I know that there are 12 inches in a foot, I can start there. I can go from feet to inches, and then maybe I can go from inches to centimeters, because that's a more common conversion. Okay? So notice, feet on top, feet on bottom. that's going to make those units cancel out. Inches are on top, so I need to have inches on the bottom. And then I'm going from inches to centimeters. I know that conversion. Okay. I can fill in my numbers. 12 inches in 1 foot. And then there are also 2.54 centimeters in 1 inch. And so again, we're just going to multiply across the top. It's just kind of a coincidence here. I probably should have picked an example that had a different number in the bottom. Because right now we're just lucky in that we can just multiply straight across the top. So I'm going to multiply 5.5 times 12 times 2.54. And I end up with 167.64 centimeters. If I did have numbers on the bottom, though, this would just create a fraction with whatever's there, and I may need to divide one more time. But it's always the same format. Get your units in the right place, write in your conversion factors, and then just multiply it out. So here's some opportunity for you to kind of check your understanding. I would definitely try these few problems on your own, and then come back and look at the answers. So you probably need to pause these videos a couple times as you go along the way anyway. This time pause and try some of this on your own. So looking at this first proportion, we're lucky, and then we've got that variable on top. That makes it a nice easy one step. I'm going to rewrite it just so it's easy to see. So remember, right now I have x divided by 3, and since I want x by itself, I'm just going to multiply both sides by 3. And I always like to think of that as 3 over 1, so I've got fractions. When I multiply this out, that 3 is going to go away. I'm just left with x on the left. On the right, I've got 8 times 3 on the top of my fraction and 12 times 1 on the bottom. 8 times 3 is 24. 12 times 1 is 12. Again, this is one of those places where I can simplify this or just do the division. 24 divided by 12 is 2. X equals 2. And the next one, here our variable is on the bottom. This is where we need to use that little hint I gave up above. That's going to make our lives a lot easier if we just flip both of these. So the left side becomes y over 24, and the right side becomes 2 over 6. And again, they're always going to be solved exactly the same way. I've got y divided by 24, so to get y by itself, I'm just going to multiply by 24. And I like to think of that as 24 over 1. On the left, we'll have just y, and on the right, 24 times 2 is 48. On the bottom, I've got 6. Do that division, and we end up with 8. And finally, converting meters to inches. It gives us a nice conversion rate here, so this is just going to be a one step. 2.5 meters times, I've got my conversion goes inches to meters, so meters has to go on the bottom, inches on the top. 39.4 inches per 1 meter. Multiply straight across. 2.5 times 39.4. Should get 98.5 inches.